Hi everyone, this is Group B1 from 2FH3. Today we would like to talk to you about metamaterials. To understand what metamaterials means, we need to go back to the word origin. Meta is of Greek origin, meaning behind or beyond. This tells us that metamaterials are beyond natural, where they are artificially structured to control and manipulate various electromagnetic phenomena. Natural materials are made of atoms and molecules, while metamaterials are made of a new level of organization. In natural materials, atoms are found arranged naturally in a specific manner, while in metamaterials we design our own collection of tiny structures. The structure gives the material its properties. To better understand metamaterials, we need to talk about light. We know that light is an electromagnetic radiation. Natural materials affect the electrical component of the light, while metamaterials affect the magnetic component as well, which expands the range of possible interactions. According to Snell's law, when a ray of light passes from a fast medium to a slow medium, it will bend towards the normal to the boundary between the two mediums. We can see a positive θ2 angle. We call n the refractive index, where it is also the square root of epsilon mu. As we know, epsilon is permittivity and mu is permeability. These two constants are specific to each material, and therefore by changing the structure of the material we can control the epsilon and mu values. As we can see for metamaterials, the ray bends away from the normal. Therefore, we say that metamaterials have a negative refractive index. In this picture, we can visualize how an artificial fluid with a negative index of refraction would look on the right, compared to a fluid with a positive index of refraction to the left. After we talked a little about the basics of metamaterials, we will move to discuss the recent research being done on this magnificent structure.
The significance of metamaterials is increasing rapidly, and because they exhibit such unique electromagnetic properties, a lot of research is being done around it. Amidst this advanced research is the design of thin electromagnetic absorbers. The importance of these absorbers is that they can operate in microwave, terahertz, and even visible frequencies. An electromagnetic wave absorber is in general a device in which all incident radiation is absorbed at the operating frequency that includes transmissivity, reflectivity, and scattering. Metamaterials have however allowed the development of a perfect absorber based on their high impedance surface. Metamaterials generally have a relatively narrow absorption bandwidth because of their resonant behavior. That is why these absorbers also have a small bandwidth in which actual work can be done with them. However, research is being done for more sophisticated characteristics such as larger bandwidths and even multiple bands of operations. Further investigation has shown that there exists a new class of ultra-thin polarization insensitive metamaterial structures that are able to achieve quite high absorption rates of almost 96% in the microwave spectrum. There are two mechanisms from which the electromagnetic energy is converted into heat for absorption. The first one is losses due to the finite conductivity of the metallic parts, while the second one is regarding losses due to the dielectric permittivity. The dielectric losses are actually higher by 2 magnitudes compared to the metallic losses. The metallic components are used for absorption purposes because they are technically considered to be perfect electric conductors. The absorber is implemented by an unconventional approach as it uses the electric ring resonator, also called the ERR. The x and y axes are multiplied by a scaling factor called S. The center absorption frequency can be hence downshifted or upshifted by this factor of S. The absorption curve as seen from the image, however, retains its original curvature. No scaling is applied in the Z direction because the thickness of the metal has no effect on the overall behavior of the absorber.
It is known that metamaterials can provide unusual or extraordinarily strong magnetic properties which cannot be found in natural materials. One of the applications of metamaterials is magnetic field shielding. Magnetic fields produced by power transformer stations and power cables in residential areas has to be shielded because of regulations that depend very much on the country. Since the regulations are stricter in some countries, for example Italy or Switzerland, there is a need for finding improved magnetic field shields. Recently, it has been shown that metamaterials can indeed be used to shield magnetic fields at very low frequencies. Natural materials are composed of atoms and molecules, but metamaterials are composed of sub-wavelength units, which are called meta-atoms. In order to have strong effects, metamaterials must be resonating structures. There is a problem that follows with the current design of such shields, and that is high loss and low bandwidth. This is an example of a meta-atom at low frequencies. It is composed of a 1 microfarad capacitor and 1 millihenry inductor. When the meta-atom is small enough, the external magnetic field can be assumed to be uniform. When the meta-atom is a simple LC resonator with some resistance, the total impedance and the current in the resonator are given by the following equation, where Z is the impedance, omega is the angular frequency. When the resistance is 0, the resonator produces in-phase magnetic field with the external magnetic field just below the resonance frequency, therefore enhancing the magnetic field. There is one problem, however. The idea is not economically feasible because decreasing the resistance in the coils require thicker wires, which results in expenditure for heavy, large, and expensive coils. A better alternative would be to use a second inductor in a purely passive circuit. The inductor would be connected closer to the source in the first one. To keep the frequency constant, a second capacitor is added in series as well. The resulting circuit would look like the following. However, the idea is not practical because it is not possible to design a circuit with 2 capacitors and 2 inductors in such a way that the magnetic flux has a phase exactly opposite to the magnetic flux of the source. It is known that magnetic flux density produced by the meta-atom is proportional to its current, and that the same density produced by the atom and current are in phase. To measure the performance of simple RLC atoms, they can be placed in an array. Here we have an array of 16 meta-atoms arranged in a 4x4. The large coil is the magnetic source. With this setup, it is observed that the field enhanced up to 73%. When the frequency increases, the metamaterial starts to shield and maximum shielding of 45% is achieved. Using passive LC circuits, the design does not have the drawbacks of active circuits such as having a bulkier design or needing an external power source. The new meta-atom has considerably improved shielding along with nice symmetry.
Ideas discussed earlier, it has been discovered that the magnetic field shielding ability of a metamaterial can be enhanced by adjusting 2 factors. The first one is inhomogeneity, which is when the size and the geometry of the artificial elements, which are the building blocks of the metamaterial, depend on location and space. The second one is anisotropy, which is when all artificial atoms are oriented in the same direction. Let's explore the differences between isotropic versus non-isotropic or anisotropic metamaterials. With isotropic metamaterials, shielding can occur using high or low permeability materials in the shield. Shielding with high permeability materials is based on trapping or guiding the magnetic field in the shield. However, shielding with low permeability materials repulses the magnetic field away from the shield. With anisotropic metamaterials, on the other hand, it uses low permeability materials in the x direction and high permeability materials in the y and z direction. As a result of this altered configuration, we can see an improved magnetic field shielding ability. This diagram shows the differences between isotropic versus non-isotropic metamaterials. In case A, it uses high permeability. Case B, it uses low permeability isotropic metamaterials. However, in case C, it uses an anisotropic permeability metamaterial, and as a result we can see that the shielding effect is more pronounced in part C compared to the others. Let's now cover the differences between homogeneous versus inhomogeneous anisotropic metamaterials. Having inhomogeneity additional to anisotropy improves shielding more than 10 times better than with a homogeneous metamaterial. The question is, how do we build inhomogeneous metamaterials? So we can do that by changing capacitance values, we can change inductance values, or we can use 2 inductors and move them closer together or far away from each other to change their mutual conductance. As a result, we get a much more pronounced shielding effect. This diagram shows the difference between homogeneous versus inhomogeneous metamaterials. The one on the right side is a homogeneous metamaterial, and we can see that the shielding effect is much more better than with a homogeneous metamaterial.
I will now introduce the idea of 3D stacked metamaterial arrays for energy harvesting. This idea was proposed for a more efficient way to absorb electromagnetic energy using split ring resonators. These split ring resonators, as seen on your screen now, are able to absorb incoming waves and convert them into AC voltage. This application was developed to replace current antenna models. So what is the difference between the 3D models and the current 2D models? Current 2D models are constrained by available surface area, or meters squared, where they can be placed, such as rooftops or pieces of land. This given area is known as a footprint in which the system must be fitted. The 3D models of stacked arrays gives more flexibility and freedom of design for the given footprint, or space constraints. As seen, there are different designs for the 3D model, each providing different purposes. But why are metamaterials so useful for this application specifically? This is because other energy harvesting particles degrade the device's efficiency when near others. However, the metamaterial split ring resonator actually improves the efficiency of the device when close to others. This improves not only the amount of energy stored, but the bandwidth range of waves absorbed. To test the 3D array, they used a 4x5x5 stack of traditional 2D arrays. This resulting device was proven to be up to 4.8 times more effective than the regular 2D layouts. This application will strongly impact energy harvesting of electromagnetic waves and many other energy transfer systems.